In this particular video, I want to talk about some of the theory behind the ideas, and in the next video, we're going to see some explicit examples. Indeed, what we really want to focus on right now is this whole question of convergence. If a power series is a solution to the differential equation, well, where is it a solution? On what intervals is it a solution? Now, I'm going to specifically focus about second-order linear homogeneous with analytic coefficients equations, which is a mouthful. What do I mean by this? Well, second order means we've got two derivatives here. It is a linear equation in terms of the y prime, and the y double prime. There's no y double prime squared or square rooted or sine of that, for example. Homogeneous because it's equal to 0 on the right side, but the new word for us, perhaps, is analytic. So a function is defined to be analytic on some interval if it has a convergent power series on that particular interval. For the most part in our exploration of differential equations, the a, the b, and the c are just going to be polynomials. And problem spots will be when, for example, you have to divide out by a 0. And that might be when it would fail this condition of being analytic. But technically the definition is that we have convergent power series. And because we're talking about series solutions to differential equations, that's sort of going to be the relevant term when we talk about all of our coefficients being appropriately nice. Well, differential equations are often presented in this form. One of the things we want to do first is actually divide through by a of x. That is, I want the coefficient of a of x to be 1, and that means that I get these new things, p of x and q of x, which are just b divided by a and c divided by a, respectively. All right. So now I want to make a very important distinction that will make a big difference in our theory of solving differential equations with power series. That is, I'm going to define an ordinary point. So I'm talking about some value x equal to a, and I will say that that is an ordinary point if the p of x and the q of x are both these analytic functions at the particular value x equal to a. Perhaps the most common way that this would fail is if there is a 0 of a of x that is not a 0 of b of x or c of x, so that when you divide through, you get an infinite discontinuity at that particular point. So that is ordinary points. And when that is the case, i.e. it is not ordinary, then we're going to call it a singular point. So if you have divisions by 0 that don't cancel out, you have singular points. So with that definition made, here's the big theorem that we're going to talk about in this video. Suppose that you have an ordinary point, the type that you like, to this second-order linear homogeneous solution with analytic coefficients, as we expressed in the previous slide. Then the claim is that an equation of this type has two linearly independent solutions that can be expressed in terms of series. This is, in effect, an existence theorem, very analogous to many existence theorems we've seen in the past, where it says that if you have a second-order differential equation with certain conditions, then you get two linearly independent solutions. What's new about this theorem is that it's talking about the solutions being series solutions, and you're saying, well, we get two linearly independent series solutions. If it's at an ordinary point, and in a lot of our examples, a is just going to be 0 here, then the series is centered at the value of a, which means your polynomials are all expressed as x minus a to some power of m. But the big question is, well, on what interval does this series solution converge? I mean, if I plug in x equal to a, then everything in this series cancels except for the 0th term, you just get a c0, but that doesn't tell you anything. What the interesting question is when does this series converge around the value of a? And here's the real key to the theorem. It says that that radius of convergence, so it's going to tell you some interval on which we can say that this power series converges, that radius of convergence about the value of a is at least as big as the distance from a to wherever the nearest singular point is going to be. So this is going to be very important to us. If you figure out where your singular points are, then as long as you don't go to a singular point, your series solution is going to be converging. But let's see an example. I'm going to have the equation 1 plus x squared y double prime minus y plus y equal to 0. So in this case, the only problem spot, if I try to divide through by the a, the 1 plus x squared, the only problem spot is where that a of x, the coefficient of y double prime, could be 0. And so the p of x and the q of x, they're analytic everywhere except for, well, plus or minus I, because 1 plus x squared is only 0 when x is equal to plus or minus I. So notice here that I'm allowing complex numbers. That is, my singular points could be complex values. They might be real numbers as well, in which case it's a little bit easier to deal with, but they could be complex, as in this case. Okay, so let me try to expand about a equal to 0. So I'm not looking near I or minus I, I'm looking near 0. And then I'm going to imagine that I have some power series, and the claim is that this power series solves this differential equation. Now in this video, we're not going to solve the equation, we're not going to solve for the CNs, we'll do that for several examples in the videos coming up. But right now I just want to ask, well, where do we know that the series solution is going to converge? I want to put up the complex plane. This is a way to represent complex numbers. I have one axis, which is the real axis, which is the horizontal, and the imaginary axis, which I denote as I times the real line. So on this complex plane, I have the a equal to 0 we've seen before, and I have my two singular points, plus I and minus I. I can actually represent these in a complex plane in a little bit of a different way by representing them as a pair. So for example, a generic point a plus ib can be represented by the pair ab, and thus the point a equal to 0 can be represented just by 0, 0. It's 0 real and 0 imaginary. The I can be represented as 0 real and 1 imaginary, and the point minus I, 0 and minus 1. So this is just a way to represent complex numbers. Then, if the claim is to find the distance between 0, 0 and 0, 1, well, I know that difference. That distance is just 1. And therefore, by our theorem, our radius of convergence is indeed 1 as well. So this is the basic methodology. You find all the singular points. Then you look wherever you are interested in, often just a equal to 0, and you compute the distance in the complex plane from 0 out to your nearest singular point. And whatever that distance is, then you know that it converges within that distance. Let's see one more example of computing distances in the complex plane. I'm going to imagine that I've got 1 plus I as my other singular point. I haven't given a differential equation for this. I'm just going to imagine that that is your singular point. Represented as a pair, 1 plus I just becomes 1, 1, and a equal to 0 is just 0, 0 again. And then when I want to compute the distance in the complex plane, well, I can just use Pythagoras. I want to figure out the straight line distance. And so, well, what is that? It's the square root of 1 squared plus 1 squared, in other words, root 2. And thus, if you had a differential equation where this was the scenario, you'd say it converged on some radius of root 2 around the point a equal to 0. If it turns out that your singular points are real numbers, then you don't have to worry about any of this nonsense, and you can just go and take the normal straight line distance between the point that you have and the singular points nearby it. Alright, so that was a little bit of the theory of the existence and the convergence of series solutions to differential equations. In the next couple of videos, we'll take a look at how to actually go through the machinery of getting solutions to differential equations using series.